How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner, and physics is my business. And our special business today is Newton's second law, the second law. Now, in an earlier program, we discussed the first law, and I showed you some dramatic demonstrations on the first part, a body at rest, and on the second part, a body moving uniformly wants to do that. Now we come to Newton's second law. This is a staggering thing in its implications and very, very difficult, really. But what students of physics learn somewhere in their course is that Newton's second law says F equals ma. And indeed, that's what it says. But that's powerful and not so easy. Let us see what Newton said for his second law. In the Latin, mutationem motus proportionalem esse vi motrici, but the Latin is a little old-fashioned, so if we look at the English, here it is. Change of motion is proportional to force applied and takes place in the direction of the straight line in which the force acts. So, let me demonstrate Newton's second law. Here I have two carts, a heavy one, a massive one, and a less massive one, and they are connected with a pseudo-spring, an array of rubber bands, which are called elastic bands, but which incidentally are inelastic. Now they are on wheels so that they move rather freely, but we learned earlier that this one has less inertia than this one. Now, when I pull them apart and stretch the spring between them, the same force acts on both. And let us see if we cannot at once predict what will happen. If we apply Newton's second law to the forces acting on these cars, clearly the big car will have a little acceleration and the little car will have a big acceleration. That's an obvious thing to speculate on. Watch it. I'm going to pull them apart. There is one and the same force acting on both cars, and you will observe that the smaller one gets going the faster sooner, of course. And so, here is an expression mathematically that describes this. And what do we learn from that remark? We learn that the accelerations are inversely proportional to the masses. The bigger the mass, the less the acceleration. Now, this experiment with the two cars, very important for our concern later, because we will talk in subsequent programs about the energy possessed by each car and about the momentum possessed by each car, and we shall learn then that Newton's second law has enormous implications for later work in physics. Now, more about the second law. Here is a scale on which I hang a weight. And I don't care what the scale reads, it reads something. We say it reads the weight of the body, but I really don't know what that means. Nor did Newton, because as we believe, gravitational forces, the earth pulls on this, stretches the scale. But remember, even Newton said, I offer no hypothesis concerning gravitation. Now, do we understand it today? But anyway, this scale reads the weight of this. So I'm going to write Newton's second law saying that very fact. Here it is. F equals mg, where mg is the weight of the body. Now I'm going to accelerate this system upward. And I want you to see what the scale does. Watch it now. The scale read more. And so I have to add here ma. In other words, the scale reads not only the rest mass of the body, but an additional force which was required to accelerate it upward. Let me now start again in the zero position, the system at rest, the scale reading the so-called weight of the body, and let me accelerate downward. Watch it. The scale reads less, and so I write minus ma, mg minus ma. And this tells us a wonderful thing, because if I were to go to the edge of my roof and hold this like this, and then let go of it here, and the whole thing fell down toward the earth, a good question to ask is, what would the scale read during the falling? And the answer is obvious. Since the acceleration downward would be that of a freely falling body, the scale would read 0. So if I should jump off from my tabletop while I am in flight toward the earth, I am weightless. I am weightless. Now, this second law bears on the first one, which I showed in an earlier program. You remember that I had an enormous weight here, on which I pulled gently with a string, and the string held it. But when I gave the system a sudden acceleration upward, the string cannot endure it. And I said then that the body wishes to remain at rest. I now add an additional fact, that the string must exert a force not only equal to the weight of the body, but an additional one to accelerate it, which it may not be able to do. No, it couldn't do it. Now, what is the meaning of this for other things? Supposing I had an enormous sphere, such as I have here, a steel sphere, 2 inches in diameter, and then a teeny-weensy one, and I want to show you that. I want to show you that. In fact, here I have several of different sizes. There's one, there's one. Very good. Now, I have one in here that is so tiny, in fact, that I can't see it without my glasses. That shows you how tiny it is. And I wonder, if I get the other debris out of the way, can the camera get that little one? Right. Well, it's there. I assert it is there, even though you cannot see it. Oh, yeah, it's awful tiny. And what am I going to say about it? Supposing I hold these two, I won't hold the tiny one because you can't see it. Supposing I hold these two at the same horizontal level, above the level of the earth equally, and I let them go. They fall with the same acceleration. Proof. Newton's second law. Proof. F equals ma is the generic expression for Newton's second law. Now, what is the F acting on this body? The F acting on that body is its weight. And when I let it go, what is its acceleration? It has a certain mass m. Its acceleration is g. So these two equations, you see, this the generic one, F equals ma all over the universe, so we think, and W equals mg for earth-dwelling creatures who wish to look at the weight of a body. So you can see that if I double the mass of any body, I would at once double its weight, and its acceleration remains unaltered, which is a sort of explanation why all bodies have the same free fall acceleration, as Galileo showed in the 17th century. Now, this is quite remarkable, because one is led to think, why? I can't believe that this one will not fall faster than this one, and this subject is taken up very excellently by Galileo in his dialogues concerning two new sciences, where I urge you to read the discussion between Sagredo and Salviati and Simplicio. Now, there are some further implications of the second law which have some levity. I like physics in cartoons, and here is a cartoon that I recently saw. Here is a little boy, and there is a bathroom scale, and here is another little boy, and they weigh, by all looks of things, about 70 pounds. Now, it's obvious what has happened. This one jumps down onto the scale. And what is the caption under the picture? Wow, he says, wow, 140. You can see that this is Newton's second law. F equals mg plus ma because of the force delivered through his acceleration to the scale. And I think that's terrific. Let's consider another such problem. Here is a smooth pulley fixed, say, to a solid beam up there. And here is a rope over the pulley. And here one man stands holding the rope and here an identical weighted man stands holding this rope, and they are both on the ground. Question: the man A climbs the rope. B just holds on. He just stays there. Question: what happens to B? Answer: B gets a free ride, for whatever A does is felt by the rope and in turn by the man, and so this is really Newton's second law. Two men on a pulley. Now, a more dramatic event, much more dramatic. Here is a scale which reads from 0 to 2,000 grams, and I put 1,000 on it, and clearly the scale reads 1,000. If I put 2,000 on it, at rest, remember, at rest, the scale reads 2,000. Now what am I going to do? I am going to put the scale on a horizontal plane on that board in such a fashion, with a pulley here and a rope, and a pulley here and a rope, and I'm going to put 1,000 there and 1,000 right there, so that I have 1,000 pulling to the right and 1,000 pulling to the left. I'm going to do that right now. There's 1,000 on the right, and I've got to hold that. Now I get over here and I put 1,000 on the left, and then I cover it over, as I like to say for my students, so that evil eyes do not see it. And remember now, we ask the classic question. When I had 1,000 on the scale in the vertical line, it read 1,000. When I put 2,000 on it in the vertical line, it read 2,000. We want to know, what does the scale now read? 1,000 pulling to the right, 1,000 pulling to the left. Several answers. One: oh, says somebody, it reads 0, since the forces annul each other. No, no, says somebody else. 1,000 to the right, 1,000 to the left, it reads 2,000. And I must tell you that whatsoever your point of view, these are both wrong. So I could leave it as an exercise for you to do, but since I have a kind heart, I will tell you that the scale reads 1,000 grams. But having told you this, I urge you very seriously to explore why that is so. One further little comment. Oh, I want you to see another picture of Newton. I showed an earlier photograph in his later years, and here is one as a young man, 17 years old, when he entered Trinity College in Cambridge, a genius the like of which the human race has not yet again seen. One last experiment. Newton's second law. Here I am going into an elevator on the ground floor. The push of the floor of the elevator when it rests is my weight plus the weight of the bag. Now the elevator accelerates upward. You know what happens. Your knees buckle and the load is pulled out of your hand. No, not pulled. It wanted to stay at rest. It was at rest, and that's what it tried to do. But what is the explanation of the added tension in my arm and the bending of my knees? Answer: F equals mg plus ma. Now the elevator is on an uppermost floor and starts down. You know what happens? Your belly feels empty. F equals mg minus ma. And so we have a better understanding of the laws that envelop us by applying the laws of Newton. And I thank you for your attention.